Hello everyone, today I am going to show you about the manual calculation of design seismic load using static analysis and doing the static analysis in a STAAD.Pro software. And for this we have a question here. Consider a 4-story reinforced concrete office building as shown in figure. The building is located in zone 5. As you can see here, the soil conditions are medium steep and entire building is supported on a raft foundation. And here the most important things we need to know is weight, which is defined here. The load weight due to the dead load is 12 kilonewton per meter square. It's a floor load, and 10 kilonewton per meter square on the roof. The floor are to cater for a live load of 4 kilonewton on meter square on the floors and 1.5 kilonewton per meter square on the roof. Determine the seismic load on the structure as per IS 1893 recommendations. So the plan and elevation of the building is as shown in figure, and I will attach this PDF in the description below. You can check the link there. And this is in x-axis, it is 4 having span of 5000 mm, and in y-axis each frames are spaced at 5000 mm. And this is the elevation view, and the first story is 4200, second story is 3200, and altogether it's a 4-story building. So we need to calculate the total area of building, and it is 15 into 20, and that is 300 square meter. Since the live load is 4 kilonewton per meter square according to IS 1893 2016, only 15% of live load is load at the floor is needed to be considered while calculating the seismic weight. At roof, no live load is considered. So we'll calculate the floor loads, and W1, W2 and W3 is calculated by multiplying area with the dead load. And for roof, and the dead load is given as 10 kilonewton per meter square. So converting every load into point load format, finally we add all of it and we'll get the total seismic weight of the structure. Now we need to calculate fundamental period, that is a time period, and according to our case, lateral load resistance is provided by moment resisting frame infilled with brick masonry. Hence we use the formula T equal to 0.09 H by under root D, and it is obtained from the clause 7.6.2 of IS 1893 part 1. By using this formula we will calculate the time period, and here we got it is 0.28 second. The building is located in type 2 medium soil. So from the again figure 2 of IS 1893 we got SA by Z value is 2.5, and in this way we can calculate AH. This is the formula for calculating AH, and we got 0.09. And design base shear value can be calculated using formula AH into W. Every formula are defined on IS 1893 part 1, which is an Indian standard code for earthquake resistance building design. And finally we got our BV, that is base shear is 1404 kilonewton, and base shear is a force which is likely to act on the building. And how it, and similarly for earthquake load in y direction, we can calculate time period as 0.32, and SA by G is also same value from the codes. And therefore conclusion, for this building the design seismic force in y direction is same as that in x direction. So we'll take this value, and in both direction the design seismic force will be same. Here is a table, and this is for story 4, and HI square, W1 square, that QI is storage here. So it is same for both x and y direction. and later I will show you in STAAD.Pro. The base here is same for our building. This is the formula. In this way we can calculate the storage here value. Hello everyone, welcome, and now I'm going to show you to solve the same problem by using STAAD.Pro. Here in this problem we have calculated the design seismic force by using static analysis, and it is a manual method, and we can solve the same problem using the STAAD.Pro. Here this is the plan view and this is the elevation view of the buildings, which we are going to find the design earthquake force. So let's now I will start STAAD.Pro VATI. Let's create a new project. Let's name it, and I'm saving it in my folder. Close this, and now let's model the same plan in STAAD.Pro. This is our plan view. Here you can see every frames are 5,000 mm away from each other in the x directions. So I will do here there are 4 span. Now it is all right. So I'm making the plan. In the y-axis as shown in figure, there are three numbers of spans with 5,000 mm each. You can measure it whether it is correct or not. The overall area of this plan, which we are going to do, is having a length of 20 and a width of 15 meter, and so the overall area is 300 meter square. Now I will make the elevation of this plan. So for making the elevation in STAAD.Pro, I need to select all the nodes, and the first floor is having 4200 mm. We need to use transitional repeat and click on link steps, and it is created. Now join every node with the beam cursor, some screen. It is the fastest method for drawing the same parallel kind of beam, and similarly for this also. Ctrl C, Ctrl V, click on reference point and select the node. In this way we can create beams very fastly. Okay, alright, now everything has been set. So we need to complete our elevation view. For this, I am again using transitional repeat along y direction. What is this is remaining story are 3.2 meter height. 3.2 meter. These are there. Link steps. Click OK. Now our frame has been created. So first of all, we'll give the support. And select all the nodes and do the sub one, and meanwhile check it in isometric view. Support has been assigned and it is a fixed support. Now we need to define the load cases, which is very important for us. I am defining earthquake loads at first. Earthquake in x direction, earthquake in minus x, or earthquake in plus z, earthquake in minus z, let us say, and then we will define dead load and live load. And this is the pattern which is followed by most of the structural engineer. Now we'll define the floor load. Referring to the problem, it is said that the long to weight due to dead load is 12 kN per meter square on floor and 10 kN per meter square on roof. So minus 12 on all the floors means floor from 4.2 y coordinate 4.2 to this much for all floor 10.6 floor load is minus 12. Floor load has been added. Similarly, for roof, floor load of minus 10 is added with the coordinate of the roof 13.8. This is the limit. So this is for floor, top floor, right? Now according to the question, live load is given as 4 kN per meter square on floors and 1.5 kN on the roof. So this is also floor load, minus 4 kN on all the floor except roof, 4.2 and 10.6, 4.2 and 10.6, and click on add and check it. Excluding roof, the live load is defined on all the floors. Now finally define live load to the top floor as well, 13.8, maybe. Let us check the coordinate again. Yeah, right. Yeah, add it. Now let's see, the live load has been applied to the structure as well. And now we'll define the earthquake. It is a static analysis. In question it is given that the building is located in seismic zone 5 and the soil conditions are medium steep and entire building is supported on a raft foundation. Two conditions has been given. Zone 5 is given and frame response reduction factor is a 5 and the important factor is also given here. Input factor I is 1 and say zone 5 zone 5 is having zone factor of 0.36. Let's define everything around it. So click on generate. Now we need to define period in x direction and in z direction manually here. So we have calculated fundamental period in x direction, which is 0.28 second, 0.28, and in z direction again we have calculated here. This is the height of the building and this d is the base dimensions. In the y direction it is 15. Y direction it is 15. Yeah, in y direction it is 15 meter. So we got the time value 0.32. Let's press 0.32, add and close, right? So we have defined everything. Let's add a factor, seismic load, add seismic load -1, seismic load in z direction 1, click here, seismic load z -1, add and close everything. According to the question we have defined dead load and live load. And now for calculation of the seismic weight we need to define the same loading condition in the seismic definition portion. We can do it manually, like going to the each member weight and adding here, but I will use STAAD.Pro editor for this because STAAD.Pro editor is a quite fast and easiest way, and I am habituated with STAAD.Pro editor. So here also I will use editor and see it's easy. Let's get started with the STAAD.Pro editor. It is a powerful tool where you can fastly define everything. For the calculation of the seismic weight of the building, STAAD will understand in this way: floor in the terms of weight, and the direction and the negative sides need to be omitted and to be deleted. If you have any doubt, ask me in the comment below. Direction and the sign, that is GY is the y direction, global y, should need to be deleted for defining the seismic weight of the buildings. So I have defined everything. Now I will save it. If any errors will come, then it will appear here. Now there are no errors. I think we have defined everything. Let's check our manual result with our STAAD.Pro result. Alright. Let's assign the material to our view. Now we have defined everything, but let's check the load case here. I think in the question it has given only 50% of the live load is launched at the floors. At roof, no live load is to be considered. So in seismic weight calculation, I have considered the roof load also, which is not needed according to the question, so I will delete it now. And this is also 50%. 50% of 4 is 2 kilonewton, and I'll change the value. This can be done by using STAAD editor or just by this method, which I am doing right now. And now add the material property for a demo purpose. Just type it 230 because without typing the material property we cannot do the analysis in our STAAD.Pro. So we need to define it. Let's see the output file. The result is generated. Now we'll check our manual calculation with the STAAD.Pro calculation as well. So let's go below, and every coordinates and calculation are given here, but base shear, what our intention is to see the base shear value which STAAD.Pro has calculated for us. So let's see here SFSG value, and the base shear calculated by the STAAD.Pro is 1404, which is equal to the value which we have calculated manually as well. These are the 4 EQX, earthquake in X direction, this is in minus X, and this is earthquake in Z, and this is earthquake in minus Z direction. So let's see the storage here. This is at 4.2 meter, that is at zero level. The storage here is 77.205. So let's check with our manual calculation. Let's see here, this is our first storage at the height of 4.2 meter. We got value of 77 and it is correct. And at 7.4 meter, we got value of 239.669, right? So it is also correct. At 10.6 meter, we got 491 in our manual calculation. Let's compare it with the STAAD.Pro. 491.786. Yeah, it is also correct. Finally, at the height of 13.8 from the ground level, so the storage shear value is obtained as 595 from the STAAD.Pro. So in the manual calculation also it is 595.358. so almost all of the value are matching here. So this is one demonstration of seismic weight calculation using static analysis by manual calculation as well as by using the STAAD.Pro for the calculation. So I think all the calculation are same, and finally my intention was to show the manual calculation versus the STAAD.Pro calculation, and I think you all got the concept, and in this way you can solve for any other problem. Thank you for your time, and thank you for listening.